Okay, so for number 26, as an apple is thrown vertically into the air, its height h and feet above ground at time t in seconds is given by h of t is equal to negative 16t squared plus 48t. So we have to find t when h of t is equal to 0. And then it asks what's happening the first time and the second time. So what we're going to do is, if we want where h of t is equal to 0, and we know h of t is equal to the formula it gives above, then what we're going to do is we're going to find where negative 16t squared plus 48t is equal to 0. So the first step we can take is, since the negative 16 and the 48 both share a t, we can factor out a t and say t times negative 16, and it will still have a t left, but 48 will not have a t left, plus 48 is equal to 0. And since we have these being multiplied together, we can basically create two separate expressions. And so we'll have this t is equal to 0. Okay, so that's one of our times, that's easy. And then we'll also have negative 16t plus 48 is equal to 0. And so that one requires a little bit of algebra, but we can do it. So that's just going to be negative 16t is equal to negative 48, or t is equal to 3. And so ask what's happening to the apple the first time h of t is equal to 0. And so when t is equal to 0, that's the first time, right? That's just, let's say, when t equals 0, the apple is being thrown. And you can also say from the ground. And then when t equals 3, that's when the apple is hitting the ground again, or it's coming back to and hits the ground. T equals 3, the apple comes back down and hits the ground. And hits the ground. Okay, so on part B, I'm just going to draw a little bit of a visual so we can see kind of the motion of the apple. So it starts at 0, and then that is not at 0. Let's try that again. So we have a graph, and it starts at 0 and comes, and we know it hits a max before coming back down, right? At t equals 3. And so it asks what time it reaches the maximum height. Well, this is basically symmetrical, right? So we know that the maximum height is going to be reached at half the time between 0 and 3, right? So all we need to do is divide 3 by 2 to get its halfway point. And so that's going to be at t equals 3 over 2, or 1.5 seconds. And so then it asks what the maximum height that the apple reaches, and so we just have to plug in 1.5 for t, right? So then we'll just say h of 1.5 is equal to negative 16 times 1.5 squared plus 48 times 1.5, which gives 36 feet. So these are two answers. Okay, so on number 27, it asks, suppose a quadratic function has the following properties. What are the domain and range for this function? So the function has zeros at negative 2 and 8, and then a vertex at 3, 12.5. So if we kind of graph this out, we have 3 points, right? And we know it's going to be quadratic, so we have to find a way to connect those 3 points. So I'll just say here's negative 2, and we have a point here, and then over here we have 8, because that's another 0. And then it has a vertex, or max or min, at 3, let's just say 3, 12.5, 12.5, 3. And so we have to find a way to connect all these points. Well, if we're trying to connect it, the way that I see it is that it looks like that, which means that the graph has to be going down and has to kind of be making a behavior like this. So if we look at the domain of this function, well, it's kind of nice. It just is going to be negative infinity to infinity. It can be anything. But for the range, since it's making this downward kind of shape, we know that our maximum is just going to be right here at 12.5. And so this is the biggest it can get. It can go way lower, so it can start, our range starts at negative infinity, but the maximum it can get is 12.5 included. Okay, so on number 28, it says suppose a quadratic function intersects the x-axis exactly one time. Explain what must be true about the values of a, h, and k. Okay, so if we think about this in graphic terms, if we take a look at the number 27 graph, it intersects the x-axis twice, right? And even if like our vertex was a minimum, let's just say it's like down here, it would still have to cross the x-axis twice, right? But if the graph lies on the x-axis, then it can only intersect the x-axis one time. So we say that the vertex must lie on the x-axis. So, which means k must equal 0, because it equals 0 on any point. And then, let's see, h can be any number, since it's like left and right, so we could like put the graph right here and it would still just be on the x-axis. And a can be any number. Except for 0. So on number 29, we have to find each of the following for the polynomial, this f of x. And so we have to find first the leading term in degree of f. Well, we know that the leading term is just the term with the highest degree. And so if we look at each of these, we have 4x is the biggest term in this parentheses, and 3x is the biggest term in this parentheses. So then what we're going to do is that just becomes the polynomial for the biggest term is -5, we can't forget that scalar, and then times, so we have a 4x to the 5th, so that's just going to be, if I do this right, that's 4 to the 5th, which is 1024 x to the 5th. And then also 3x squared. So if we square that 3, that just becomes 9x squared. And so once we add all these terms and multiply these terms together, it's -5 times 1024 times 9, which gives, okay, our leading term is going to be, -46080 x to the 7th, and its degree is equal to 7, because whenever we multiply terms, we add their exponents, right? So that's just 5 plus 2. Okay, So if we're looking at the zeros, remember what we have to do, and I'm going to take this stuff away. Uh-oh. Let's take the eraser, take all the stuff away. Okay, so we're going to look at each parentheses with the equations in them. So to find the zeros, we have two different equations. We have a 4x minus 3 is equal to 0. So if we solve our first equation, that'll be x is equal to 3/4. So here's one of our zeros. And we'll have a certain multiplicity. And then we'll also have a 3x plus 1 is equal to 0, or x is equal to negative 1/3. So for the multiplicity, I'm going to rewrite that. Multiplicity, we just look at the outside of those parentheses and see what power it's being taken to. And so for the 3/4, it has a multiplicity of 5. And then for the 3x plus 1, it has a multiplicity of 2. And so this just becomes our answer. Okay, so for part C, this is actually where our part A will come in handy. So we have to basically describe the end behavior of this function that we're given, right? And so since it's an odd function, because it has, it's to the power of 7, which is odd, its end behavior isn't going to be the same, right? If we had even, we would just say it's either going to negative infinity for both x infinities, or it's going to positive infinity. But this one is going to have opposite behavior, right? And so that is kind of our telltale sign for our degree. And now we have to look at the leading coefficient. And so our leading coefficient is negative. So that means kind of it's reflecting, right, over the x-axis. So that means that it's going to be doing kind of the opposite behavior of what we usually think it does. And so usually if we were given an odd function, as x goes to a negative infinity, f of x would go to negative infinity too, right? But this negative leading coefficient actually flips it for us and says, actually, f of x is going to infinity. And since this is an odd power, this makes this other term easy because, like we said, it's going to be the opposite. So as x goes to infinity, f of x is going to go to negative infinity. Okay, so for number 30, we just have to find a formula for a polynomial with the following characteristics. Write your answer in factored form. So it has to be a degree of 3, has to have zeros, -5, 0, and 2, 0, with no other unique zeros. So what that means is, like, we basically can't make another, like, parentheses. I'll show you what I mean as we go through the problem. And it also has to pass through the point 1, 3, and have an end behavior of as x goes to negative infinity, f of x goes to infinity, and as x goes to infinity, f of x goes to negative infinity. So let's just start with one of the most important things is the degree and its zeros, right? So it has to have a degree of 3, so that means with zeros, -5 and 2. So our function is going to start to look like, we know it's going to have an x plus 5, and then also it's going to be multiplied by an x minus 2. And now, if we just left this like this would only be a degree of 2, right? Because it's just x times x. And so what it means by no other unique zeros is that it means you can't multiply an x minus 1 to get the degree of 3 that you need. And so what we have to do is we have to create a multiplicity. And so we can do that by just adding a squared term with one of these parentheses. So let's just do x plus 5 squared times x minus 2. And so right now we've kind of checked off our degree of 3 and has zeros through this. And also I'm just going to do a y equals. And if it has to pass through the point 1, 3, that means we're going to have some kind of scalar quality multiplied with this, right? So then we can just solve for this a, or this scalar quality, by plugging in that point. Just say 3 is equal to a times 1 plus 5 squared times 1 minus 2. So then that gives us an a of, looks like negative 1/12. And so then our formula, so now we pass to the 0.13. So our formula becomes negative 1/12 x plus 5 squared times x minus 2. And so if we are trying to verify its end behavior, it says, so since it's odd, we know that, f of x is going to be doing two different things for the different x end behaviors. So we got that down. And it says as x goes to negative infinity, f goes to infinity. So that would mean that we have to have a negative a out here, right? Because it's kind of the opposite of what we would expect it to do. And so that has been verified. We got a negative a out here. So we are perfectly a-okay to have this be our formula. Okay, so on number 31, we are given this polynomial, and we got to do some things with it. And so on part A, it asks us to write P as a product of linear and irreducible quadratic factors. So linear just means we can't have like x cubes being multiplied with each other, x squared or whatever. And so let's try and simplify this polynomial as best as we can. So the first thing I see is all of these terms share a 2, right? So we can, and just because I don't like having a negative with being multiplied by the leading term, let's just factor out a negative 2. So then if we do that, we'll have x to the 4th minus 6x squared plus 5. Okay, so now this is kind of like an x squared function, right? Where we have like x squared plus some x term plus some constant. And so actually what we can do is we can factor out this, because what multiplies to give 5 and adds or subtracts to give us negative 6, well, that's negative 5 and negative 1, right? So then we can reduce this down even further to x squared, remember, because we got this x to the 4th, x squared minus 5 times x squared minus 1. And remember, this is difference of squares, so this can even factor for us too. So difference of squares tells us that, and I'm just going to write this over here, hopefully you can see this. That just means that, I'll write that negative 2. Okay, so difference of squares, we have a squared term being subtracted by something else that can be squared, and so we just take the square root of both of these, so square root of 5 and square root of 1, and multiply them by each other. So I'm going to start out with the 1, because that one's a little bit more recognizable and a little bit easier, but that's going to factor out to x minus 1 times x plus 1, and then that 5 is going to factor out into x minus a radical 5, because remember we got to square root it, times x plus radical 5. And so this is as far as we can simplify it with linear and irreducible quadratic factors. So if we're looking for all real zeros of p, we just have to take all of these factors and like set them equal to 0 and solve, right? So if we do that, we'll get x is equal to, well, we're going to have a negative 1 and a positive 1, so plus or minus 1. And the same thing happens with the radical 5s. So x is going to be equal to plus or minus radical 5. Okay, so on part C, we're supposed to make a rough sketch and include the zeros and end behavior. Okay, so let's just keep our end behavior in mind. We know that, so for negative, x goes to negative infinity and x goes to positive infinity, since we got an x to the 4th and that's an even power, we know that the end behavior has to be doing the same thing, right? And because we got a negative 2 being multiplied by that, that means that it's going, both sides are going down to negative infinity. So we got to make sure about that. So And also, let's mark the zeros as well. So we have zeros at radical 5, negative radical 5, and positive radical 5. So that's like, I'd say about right here and about right here. And then we have zeros at negative 1 and positive 1. And so since the end behavior is negative infinity, as x goes to negative infinity, we know we're going to be coming up, right? So we got to be coming up. And then we can kind of do whatever we want here, but we know we have to come back down. And then we know we're going to have to come back up here. And then we can come back down here to make sure the end behavior is the same. So there you go.